Welcome back. Last session we had seen problem number 9 and we got the answer A. Okay. Now let's solve problem number 10. Every problem is a different problem, right? But there are some problems if you solve one type of problem, other problems are straightforward. Okay. Problem number 10. In the silicon BJT circuit shown below, assume that emitter area of transistor Q1 is half that of transistor Q2. The value of current I0 is approximately, okay. Therefore, the circuit is given. Problem number 10. Okay. 9.3K. And beta is 700. Here beta is 715. This is what is transistor Q1 and this is what is transistor Q2, and asking I0 approximately. Option A 0.52, option C 9.3 milliampere, option D 15 milliampere. Right? Just think for 10 seconds, then we will see. Saying what is I0 approximately. We didn't see the circuit before, right? That's why we are seeing now. And we are trying to solve the problem. Let me tell you one point here. Okay. Yeah, and one more thing is given. What is that? The emitter area of transistor Q1. The emitter area of transistor Q1 given. The emitter area of transistor Q1. Area of emitter of transistor Q1 is half that of emitter area of transistor Q2. What is the meaning of it? If I take the transistor Q1, right, let us say this is what is our transistor. Let me draw three-dimensional view. This is what is the transistor, okay. This is emitter, base, collector. Therefore, what is the emitter area here? The emitter area is nothing but, if I take, this is what is our emitter area, right? Are you able to visualize in three-dimensional view? Therefore, everything is having, all should be collinear, okay? That is fine. So, if you, this is what is emitter area. This is what is emitter area. 1. The area of cross section of your emitter, that is half of this Q2. Therefore, what is Q2? Q2, if I take, let us say Q2, your Q2 will be maybe it is having bigger area. This is what is the area. This is emitter, this is base, this is collector. Okay. Therefore, now what is the area now? This is AE2. Therefore, what is AE2 or what is AE1? AE1 is equal to AE2 divided by 2. Half of this area is Q1 emitter area. That is what is given, right? The emitter area of transistor Q1 is half of the area of Q2. This is what it is. Therefore, what does it mean? What is the meaning of it? Let me tell you. Let us say this is nothing but PN junction diode. Then whatever current, the voltage, let us say I am applying the same voltage. I am applying same voltage between base to emitter, base to emitter. Then whatever current you get here for a PN junction diode and whatever current you get here, this current will be twice that of this current for the same voltage. Why? Because the area of cross section is twice. If area of cross section is twice, whatever current you are getting from transistor Q1 for the same voltage, then you will see twice that of current in Q2. That is expected, right? I can prove that also. Let us say this is what your NPN transistor. When I say this is what your NPN transistor, N plus P minus, okay? And this is also NPN transistor. Basically, these two are NPN transistors, right? Then this is nothing but a PN junction diode, right? Therefore, if you take a PN junction diode, this is nothing but a PN junction diode, right? And this is N, this is P. Basically, we know this is N and P, right? Now, this is nothing but emitter and this is what is your base. Therefore, emitter and base. Now, let us apply base to emitter voltage. This is what your VBE, right? This is your VBE. And similarly, if you apply, this is what is this. Then if you calculate the current I is equal to, for a PN junction diode, right? I is equal to I naught into e to the power of V by eta Vt minus 1. Here V is nothing but VBE, eta is 1 for transistor and Vt minus 1. But what is I naught, right? Remember, then where is, in this formula, where is area of cross section? That is what is there inside I naught, where I naught is equal to A into Q into dP into Pn naught divided by Lp plus A into Q into Dn Np naught divided by Ln. This is what is reverse saturation current. When you derive the formula or PN junction diode current components, I is equal to I naught into e to the power V by eta Vt minus 1. This is what your I naught, which is constant at a given temperature. Therefore, A is nothing but area of cross section of your PN junction diode. There we are getting that I naught. Okay. Q is charge, dP is diffusion constant for a hole, Pn naught is nothing but the minority carrier concentration in N-type semiconductor, which are nothing but holes, divided by diffusion length of Lp. Similarly for N. Therefore, here is depending on A. If A is twice, then I naught is 2 times, then your current is 2 times for the same voltage. Therefore, indirectly that I naught is having the information about area of cross section of your PN junction diode. Okay. Or qualitatively I can say same voltage, but you have more area of cross section, then more number of electrons can go, then you get more current, because current is nothing but rate of flow of charge. Per unit time, how much charge can flow, that is what is your current definition. If more area of cross section, more number of carriers can cross, then more current. That is expected. Therefore, what I want to say from here is, for the same voltage, if area is twice, let us say whatever current you are having here, let us say this is what is having IE1. Therefore, the current whatever you are having, that is what is IE1. This is what is having IE1. and this is what is having current IE2. Then if you ask me the relation between IE1 and IE2, right? IE1 is equal to IE2 by 2, exactly half of this current, because this is half of the area, then whatever current you have for the same voltage, for same VBE, for the same voltage, because this area is twice of this, or this area is half of this, the current also half of this. Therefore, this is what is very important point. This is what you need to understand. This is what is our observation based on the explanation. See, we are not solving the problem, I am explaining the problem, right? Therefore, what we got to know, because the area of transistor Q1 is half of this, right? Then your IE1, the current whatever you are having here, is half of this current, or I can say the current which is what is flowing through this is twice of this current for the same VBE, Therefore, I can say or what is your IE2? Your IE2 will be equal to 2 times of IE1 for same VBE, same VBE and beta. Okay, that is fine. Same VBE, that's enough. Both are same. Okay, fine. Now take it. If you understand, I think straightforward, we can get the answer. Actually, this is nothing but current mirror. Current mirror means whatever current which is what is flowing through transistor 1, if same area, let us say same area, both are having same VBE, then both will have same collector current, provided both will have same beta. But if you observe clearly, here beta is 700, here beta is 715, because we are intentionally we want identical transistors, but because of process variation, I told you, right, no two transistors will have same H parameters or same beta. That is what is represented practically here. This is 700, this is 715. Practically you have some variation, but the variation is too less, therefore that you can ignore, and you can take beta approximately 700. Then whatever current you have, IC is approximately, you will see the here, if same area, same VBE. That is what is current mirror. Whatever current which is what is flowing through transistor 1, same current will be flowing through transistor 2. Okay, approximately. But he is asking also approximately what is I0. But here area is twice, then your IE2 will be twice of IE1. It will be mirrored, but twice. Whatever current which is flowing through Q1, same current, but into 2. That is what is Q2. Whatever current into 2. If area is 3 times, then 3 times of Q1. If area is 4 times, 4 times of Q1. If area is half of Q1. That depends on the area of your transistor. Therefore, we can get different current mirror into the second transistor based on the area of Q1 and Q2 relation. Okay, take it. over done. Now let's solve the problem. I just explained the problem, right? This is important now for us. Now, therefore, let's see. It is somewhat difficult for you, right? But the same problem can write in a different way also. See, what is the voltage at this point with respect to ground? 0 only. But what is at this point with respect to ground? Minus 10. Therefore, this is minus 10 with respect to 0. Therefore, what is the voltage drop here between this point to this point? 0 minus of minus 10. Therefore, this is what is 10. Okay. This is exactly the 10 volts. That is fine. The 10 volt is equal to the drop across 9.3K plus the voltage what you have. Therefore, now tell me, let us say there is a current which is what is flowing through it. Let us say this is what your I. Okay, that is what is your current I. Normally people call this as I bias. This is what your bias current. Okay. Now, that is fine. Therefore, now what is that I bias current? KCL. This current is equal to this current plus this current. Therefore, what is this current? This current is nothing but what? The collector current of transistor 1. Therefore, this is IC1. Then what is this current? This current is nothing but, again, two things. Therefore, this is IB1 and this is IB2. Right? Therefore, what is this? This is nothing but IB1 plus IB2. Right? Therefore, tell me what is your I bias from this? I bias is nothing but I bias, the bias current or the current which is flowing through 9.3K is equal to the collector current IC1 plus IB1 plus IB2. Therefore, IB1 plus IB2. Now, this is nothing but IC1 plus what is IB1? Can I write it as IC1 by beta? IB2, can I write it as IC2 by beta? This is beta 1, this is beta 2. What is beta 1, beta 2? Beta 1 is 700, beta 2 is 715. They are very high value. Therefore, what does that mean? This IB1 is 7/15th part of your IC1. IB2 is 7/15th. Sorry. Yeah. This is 700 part of IC1, 7/15th part of your IC2. Therefore, you can take them 0. You can neglect with respect to the collector current. Therefore, what is your I bias? I bias is nothing but IC1. I bias is nothing but IC1. Therefore, the current which is what is flowing through 9.3K is nothing but almost the case. We are neglecting the current with respect to IC1. Majority of the current is flowing through the transistor IC1. Whatever current IC1 is flowing through Q1, right? This is equation 1. This is I bias. Okay. Equation 1. Now, whatever current which is what is flowing through Q1, the same current also will flow through this, provided both are having same area. We know that both are having same VBE1, right? Therefore, what is this voltage? This is what is your VBE1. And what is this voltage? This is nothing but VBE2. Both are having same voltage or not? Both the emitters are shorted. Both the bases are shorted. Therefore, both are having same VBE, right? Therefore, we know that, or we observe that VBE1 is equal to VBE2. If VBE1 is equal to VBE2 and what else? Same base current is flowing. If VBE1 is equal to VBE2, same base current is flowing, let us say, then what about this current? IC1 will be equal to IC2, right? Let us say, what is I0? Therefore, let us say this is IC2. This is nothing but your IC2, right? IC2 is nothing but your IE2, what it may be, right? And you observe that, and what is area of Q2? Area of Q2 IE2 is equal to twice of area of E1. That is what is given. Therefore, what is that? IE2 is equal to 2 times of IE1. What is that? What is IE2? IC2. IC2, because beta is very large. IC2 is equal to 2 times of IC1. What is IC2? Your output current I0. Therefore, I0 is equal to 2 times of IC1. What is IC1? I bias. Therefore, because that's what I told you, current mirror. Whatever current which is what is flowing through the transistor 1, same current will flow through transistor 2 provided same area, but here it is having 2 times of the area, that's why 2 times of the bias current or the collector current what you are seeing in the transistor 1. Right? Now, if you know I bias, problem is over. How to find I bias? Just listen, I'll give you time to write down. To find I bias. To find I bias. Definitely this problem is related to DC analysis. Remember, if the problem is related to DC analysis, we need to deal with KVL equations. Write down KVL equation. What is KVL? The voltage at this point with respect to this point is nothing but 0 minus of minus 10. This is nothing but 10, or you can write loop KVL, but instead of this qualitatively this is better. 0 minus of minus 10. 10 volts is equal to drop across 9.3K plus VCE1. Therefore, 10 is equal to drop across 9.3K, which is nothing but I bias into 9.3K plus VCE1. What is VCE1? If you take the transistor, this is what is the transistor, this is base, collector, emitter. What is VCE? VBE only, right? Actually, this is your VBE. And this is nothing but your VCE. Because collector and base are shorted, what is VCE? VCE is nothing but VBE. Because collector and base terminals are shorted. This is what is called diode connector transistor. Why it is called diode connector transistor? I will explain after solving the problem. Therefore, this is what? 10. Therefore, the equation implies 10 is equal to I bias into 9.3K plus VCE1 is nothing but VBE1. What is VBE1? The base to emitter voltage. Because that is nothing but what is given here? That is silicon BJT. When I say silicon BJT, what is VBE? 0.7. Therefore, this is nothing but I bias into 9.3K plus 0.7. Therefore, what is I bias? I bias is equal to 10 minus 0.7 divided by 9.3K, which is 1 milliampere. That is I bias. But what is I0? Therefore, I0 is equal to 2 times of I bias, which is 2 milliampere. This is the answer. Answer is 2 milliampere. This is what is. Remember, this is current mirror. The current whatever which is what is flowing through transistor 1, the same current will be flowing provided same area. If area is twice, 2 times, area is thrice, 3 times, area is half of the current. Okay. Whatever current you want, you can get it by choosing the proper area of transistor 2 with respect to Q1. This is what is current mirror. The current will be mirrored with some factor. This is what is the circuit. Okay. Take it. Remember, this is one of the powerful circuits people use in analog circuit design. Why it is so powerful? Whatever current you pumped in transistor Q1, the same current will be carried to Q2, assume that same area. Then if you take one more transistor with the same VBE, right? Then if you choose different area for different transistors but having same VBE, remember, you will get different currents in different branches. This is what is kind of current bias. We are biased in the, we will bias other circuits with respect to this circuit. And if IC1 is fixed irrespective of temperature, process variation, voltage variation, then in all branches your current will be fixed based on the ratio of the areas of transistors. Okay, that is so powerful. But how to make this IC1 constant? Sometimes instead of 9.3 kR resistor, people put a current source, ideal current source. But how to get that ideal current source? That is different. But if you put ideal current source here, then it will be always constant current. That constant current will be mirrored to so many branches. Okay, depends on area. Therefore, the current is shipped to, if you want to ship any current from one point to like the longer distances, this is the best technique to ship. This is what? Because the voltage is converting into current. The voltage will be adjusted automatically across the PVT variation, process voltage temperature variations, because whatever current you are going to bias there, that current is the one which is what is going to adjust the VBE. If that current is constant, then irrespective of PVT variation, the VBEs will be adjusted, then you will get different currents in the different branches. Okay? What are maybe? That is what is current mirror. Whatever current you have in transistor Q1, the same current will be in Q2, provided same area. Over? Okay. Now why it is called diode collector transistor, I will explain, then we will go to problem number 11. Now problem number 11. The voltage gain of the circuit shown below is 10K, 100K, 12K. Option A, mod AV is equal to 200. Option B, mod AV is equal to 100. Option C, mod AV is equal to 20 approximately. He has given approximately. Option D, mod AV is equal to approximately 10. Am I correct? 200, 200, 100, 20, 10. This is GATE 2012 for 2 marks. Okay. This is what is given. Fine. Just think for 10 minutes, sorry, 10 seconds, then we will see. Okay. Maybe after solving this problem, the session will be over. Then we will see next problems from next session. Okay. I think this is the last problem in this session. Think about for 10 minutes. What is asking for? Asking for voltage gain. What is voltage gain? I can give you directly the formula. You can use it. But let's see. AC analysis or DC analysis problem. The circuit is given, but asking whether it is AC analysis or DC analysis. Surely AC analysis, because asking for voltage gain. Therefore, asking for voltage gain. AC analysis. Then short circuit, short circuit, short circuit. Now the load is 12K, but actually if there is inductor, this is connected to base bias circuit for DC analysis, but there is no inductor. Okay. If there is no inductor, this feedback resistor will act as a negative feedback component, and that will reduce the overall gain from common emitter configuration. And this is short circuit, right? And then 10K, 100K, 12K. Then just think about it. What is this configuration? It is common emitter amplifier with feedback, which we did not see. We have seen CE with RE amplifier where RE that was providing negative feedback, that also we had seen, but this circuit we did not see, right? Just think how to calculate. Okay, it takes long time to calculate for you, but actually there is a formula. You take it directly. I will derive that formula from one of the circuits using feedback configuration. Okay, the formula is actually this is what is RB. Wherever you have this, right, you can use this formula. This is what is your feedback resistor, we call it as RB, and this is nothing but your source resistance RS, and this is your RC, and whatever load you connect, that is RL, right? Then what is voltage gain? See, if you take CE with RE amplifier, if you take CE with RE amplifier, only AC circuit in the sense AC configuration, this is RE, RC, VCC, and this is your input voltage, output voltage. Capacitors are there, but they are shorted. Therefore, now what we got? We got V0 by Vi. That is nothing but voltage gain, AV, which is approximately what? Minus RC by RE. That is what we got, right? Ratio of resistors. And I told that this is stable because of negative feedback, right? Because of negative feedback, your gain is stabilized, but it is low value. But what are the ratio of resistors? Similarly, if you ask me what is voltage gain of this is also having feedback, but connected to base feedback. Therefore, AV is approximately equal to minus RB by RS. It is also depending on ratio of resistors. You have to remember this formula, which I did not derive, but I will derive. Therefore, this is what your voltage gain, which is already derived. That is nothing but CE with RE amplifier. Okay? But here, why we didn't derive and why we didn't see this before? Here, if RE is there, then we are getting minus RE by RE. If you don't want RE, we can use bypass capacitor. That's what we used, right? But here, if you don't want RB, we should use inductor. I told you, right? We don't want to use this circuit. That's why the circuit is not so popular. Every time we have this only. But what about maybe theoretically for your understanding purpose, if you ask me what is the voltage gain, the voltage gain is nothing but minus RB by RS, which is ratio of resistors. Then tell me what is this value? If you know the formula, RB value 100K, RS value 10K, KK will be cancelled. This is nothing but minus 10, but asking for magnitude. Therefore, what is mod AV? Mod AV approximately 10. Therefore, what is the answer? Qualitatively also I can say a little bit. This is what is having negative feedback. If it is having negative feedback, the gain will be lesser. Definitely gain won't be 200. Gain won't be 100. Maybe you can say either 10 or 20, right? Because if you apply negative feedback, your gain will reduce. If gain is reduced, surely your gain will be in the order of 10, right? Therefore, you can say option D. But there is a formula. The formula is minus RV by RS. The feedback resistor divided by the source resistance RS. Take it. Over? Okay. We have to compare with this, then we will see. Now write down problem number 12. Actually this we already solved, right? But we can go very quickly. Is this over? Okay. Now problem number 12. Just go through it. We had seen this already. We solved one of the problems related to that. But asked in a different way. This is GATE 2014 set 1. What is that? If the emitter resistance in a common emitter voltage amplifier is not bypassed, okay, then it will, option A, reduce both voltage gain and input impedance. Option B, reduce voltage gain and increase input impedance. Option C, increase voltage gain and reduce the input impedance. Option D, increase both voltage gain and input impedance. We have seen, right? If the emitter resistance is not bypassed, means CE is removed. If capacitor CE is removed, we already had seen this, right? What is that? If CE is removed, then surely your voltage gain will decrease because negative feedback, and your input impedance will increase, right? Therefore, what is the answer? Reduce the voltage gain and increase the input impedance. Okay. Maybe if you go back some problem, I forgot the problem name, but problem number. But if you go back to that, it is the same. Both are same only. If emitter resistance in a common emitter voltage amplifier is not bypassed, then surely not bypassed means negative feedback. Voltage gain will decrease, your input impedance will increase. Therefore, what is that? Option A. Okay. Therefore, if you take CE amplifier, RC coupled CE amplifier, right? If you don't bypass, actually we are using bypass capacitor, right? This is CE and this is your RE, right? You can say. Then if you don't bypass it, then what you get? If you bypass it, what your voltage gain? Minus HFE into RL divided by HIE. And then what is your input impedance? HIE. This is what we have seen, right? If you bypass it, right? If CE is removed, not bypassed, then your voltage gain will be minus RC by RE, C with RE amplifier basically, and your input impedance will be HIE plus 1 plus HFE into RE. This is what it is. Okay. Therefore, here if you ask me, your voltage gain mod AV will decrease, then your input impedance increases. If you remove, if RE is not bypassed, I'm just repeating it, okay, which we had seen already. Okay, that is what it is. Here CE is there, here CE is present. There CE is not present. Okay, I think the session is over. In the next section, we will see next problems. Okay, thank you.